title of this video is Relationships. The fear of statistics will keep you average. Very funny. Engineers often fear statistics. Statisticians often fear engineers. They should talk to each other. Go and find yourself a statistician when you actually have some variables and have some data, and get them to tell you what to do with it. Scrub that. Don't do that. Before you even think about getting any data, you should be developing a relationship with a statistician, because they may have very specific ways in which you should be collecting the data, and they can give you advice around that and ideas about proper procedure and experimental design. Talk to the statisticians if you fear statistics. Whenever there's a blind spot in your knowledge, go and talk to somebody else. It's really important, because you can't know everything. Accept that there are other disciplines out there that are really deep, that take a great deal of time to learn. You don't have to know anything. Find someone who does and make that relationship. So let's have a look at some very simple relationships just to get you started. So let's say we're looking at the relationship between educated and uneducated people with respect to whether they're prejudiced or unprejudiced. We've got two different groups there. You've got two different groups there, two different sets of data. Let's have a quick look at them. Well, the first set looks like the educated are unprejudiced and the uneducated are prejudiced. It seems to be what the data is suggesting. In the second picture, we've got exactly the same numbers. So what is the relationship between? There seems to be a relationship between whether you're educated and unprejudiced or uneducated and prejudiced, just looking at those numbers, although some educated people are prejudiced. You also need to think about the relationship between the sample and the population. If you do a study, you want to be able to make general statements. You want to be able to talk about the population, but you can only do a finite number of measurements in the amount of time you have. So the attributes will be something you're looking at, the characteristics or quality that describe a person or an object. For example, male, female. The variables are the groupings or sets of attributes that can be measured or observed. Okay, so look at the relationship between the examples to get a better sense of the relationship between attributes and variables. In terms of observation time, variables occur. They occur before, they occur after other things. One's an input, one's an output. There are often relationships between things in time. What you do, what happens next, what is independent and what is dependent is really the key for all of these sorts of things. So then you can develop graphs of these relationships. For example, if you're interested in the structural integrity of a skyscraper, you might be interested in looking at the pouring rate of the concrete for the supporting walls. If the structural integrity goes up, maybe the pouring rate was slower. If it goes down, maybe it was faster. But is it cause or is it correlation? Now, in a positive correlation, as the value of the independent variable increases, the value of the dependent variable increases as well. So in this graph, we've got country education, which is independent, but then we've got the per capita income, that's variable. So as the country education goes up, generally speaking, it seems as if the income of the person goes up as well for all countries. So average education is the independent variable and income is dependent. There's a dependency on education. Let's have a look at negative correlation now. You can see that it's moving in a different direction. So this is now the level of education related to dental problems. So as the amount of time spent in education goes up, the number of dental problems goes down. So is that also related to income? Probably, but we're looking at this relationship here. So actually figuring out what the right relationship is, the right variables you should be looking at, what's dependent, what's independent, a statistician can help you with that. And you can go beyond dots on a page. There are all sorts of methods for putting lines through dots. Some of you may have come across root mean square deviation, but I'm not going to go into any of those methods here. Generally speaking, you can see that the lines fit the dots. One's for positive correlation, your independent goes up, your dependent goes up. Or negative, your independent goes up and your dependent goes down. Or there may be no relationship at all. As I said, you've got to talk to a statistician who can tell you what might be a useful way of actually finding something meaningful in your data so that you can tell that story of how you've made a contribution. Positive correlation, the Pearson coefficient is 1, negative is -1, and no correlation is 0. Just thought I'd throw that in. Talk to a statistician. They've got a decision tree. They will ask a whole lot of questions and figure out what test you need. What does the data look like? Is it correlation? What sort of test should you use? Is it independent? There's a whole lot of questions that they use to figure out what tests they're going to do. So talk to them if you're not confident. The title of this video is Performance, in particular design performance. Now, before you build anything, you can actually evaluate the performance of the design. So this can be through wireframes in the case of web design, it can be in the case of simulation, mathematical models. There are lots of doors that you can go through to investigate how something might actually play out in the real world. Let's have a look at how that works. I'm going to be talking specifically in the domain of civil engineering, but these methods can be applied to any field of engineering. So what does design for performance look like? Well, you've got some kind of criteria. You develop some designs, you apply a tool, work out how the design might satisfy that criteria. Does the criteria satisfy the specifications? No? Go back around, whip through it again. Iterate around a few times until you end up with a final design. So you do this before you've built anything at all. Let's look at some examples. So performance-based analysis is used extensively in civil engineering. You can see that within civil, transportation engineering, environmental engineering, structural engineering, all of them have analytical tools and areas of application. For example, in structural engineering, buildings and bridges. Environmental engineering, water structures, building architecture, urban energy. Transport engineering, highways, pavements, air. There's loads of different tools that you can use for figuring out how good your models are. And there are many papers that use these tools. If you're interested in these particular fields, by all means, track down those papers. And the list of abbreviations is down the bottom of the page. Various things that I've used significantly have been finite element, Monte Carlo. So again, potential applications. You look on the right, there's a whole list of things. For example, with buildings, there can be wind, there can be aerodynamics, just a whole range of things that you can actually develop tools to figure out for you. It's a really interesting area. Here's some characteristics of just the highway transportation algorithms. I mean, the amount of work that goes on in these areas is just phenomenal. But if you look across, you'll see, for a particular design, you'll see there's things around safety, there's things around specifications, there's reliability, there's all sorts of things that you typically expect to see in any kind of civil structure. The link to this particular paper is on the web, so you can go into it in much more detail and look at other sorts of applications. This is just a sample. Now note that in civil engineering, there's obviously a construction code. Australia has one, the states have them. You need to be familiar with these codes and use tools that are compliant with these codes in these sorts of areas. I mean, civil engineering isn't the only field that has codes. If you're in medical engineering, there's tons of medical regulations and hoops you need to get through, stages, phases, gates, in order to actually get a product out there. I will just point out one tool that I found particularly useful. That's multi-criteria performance, where you're looking at different options and you're analysing them with respect to different criteria and figuring out calculations to figure out which option is best. Multi-criteria decision analysis is a particularly useful tool in very highly complex and dynamic space. I'm not going to go into how that works here.